Ever look up at the clouds and wonder what's happening up there? On Earth, high-altitude winds, our jet streams, are powerful forces, shaping our weather from about 10 kilometers up. But what if I told you that on another planet, the winds go deeper, much, much deeper? Today we're journeying to the gas giant, Jupiter, to unravel a mystery that's been puzzling scientists for decades, the deep wind puzzle. For a long time, we could only see the surface of Jupiter, its iconic, swirling bands of colorful clouds. We knew it had powerful winds, some screaming along at over 500 kilometers per hour. That's faster than any hurricane ever recorded on Earth. But the big question was always, how deep do these stripes and storms go? Are they just a thin layer of weather, like on Earth, or is something more profound happening underneath? For years, scientists debated this. Some theories suggested the winds were just skin deep, confined to the upper layers of the atmosphere, where sunlight could reach. Sunlight provides energy, and energy drives weather. It made sense. But other theories proposed a much wilder idea, that the winds were a manifestation of something deep within the planet's interior, extending thousands of kilometers down, but proving it was another story. How do you peek under the clouds of a planet that's over 600 million kilometers away? The answer came from a remarkable spacecraft, NASA's Juno mission. Launched in 2011, Juno arrived at Jupiter in 2016 with a singular purpose: to orbit the planet from pole to pole, and study what lies beneath its dense cloud cover. Unlike previous missions that orbited around the equator, Juno's unique polar orbit allowed it to fly over different regions on each pass, mapping the planet in incredible detail. But Juno wasn't looking with a camera, not for this puzzle. Its secret weapon was its ability to measure gravity. Now, you might be thinking, gravity? How can gravity tell you about wind? It's an amazing bit of physics. As Juno flew over Jupiter, the planet's immense gravity would pull on the spacecraft. If Jupiter were a perfect uniform sphere, that pull would be exactly the same everywhere. But it's not. Jupiter is spinning incredibly fast. One day is less than 10 hours long, which causes it to bulge at the equator. More importantly, the stuff inside Jupiter isn't spread out evenly. And here's the key: moving stuff has mass. Those gigantic, planet-circling winds, even though they're just gas, carry an enormous amount of mass. As these colossal rivers of gas flow, they create tiny, but measurable, fluctuations in Jupiter's gravity field. As Juno zipped by, it detected these subtle tugs and pulls. It was like feeling a slight wobble in a spinning top. These wobbles were the telltale signature of the material moving below. When the data came back, it was mind-blowing. The gravity measurements revealed that Jupiter's weather isn't just skin deep. The jet streams, those famous bands we see, aren't just surface features. They extend downwards, penetrating the planet to a depth of 3,000 kilometers. Let that sink in. 3,000 kilometers. That's like the distance from New York City to Denver, but straight down into a churning, high-pressure ocean of gas. These aren't just winds. They are colossal, deep-seated cylinders of flowing gas, rotating around the planet's core. The sheer scale is almost unimaginable. The mass involved in these deep winds is equivalent to about 1% of Jupiter's entire mass. Considering Jupiter is 318 times more massive than Earth, that means Jupiter's weather system contains about 3 times the mass of our entire planet. This discovery completely changed our understanding of gas giants. The winds on Jupiter are not just weather in the way we think of it. They are a fundamental part of the planet's structure, as integral as the layers of rock inside the Earth. They are deep, powerful, and incredibly persistent. And this brings us to the next, even bigger part of the puzzle. What is powering these deep winds? On Earth, our weather is driven by the sun. Solar energy heats the equator more than the poles, creating temperature differences that drive winds. But sunlight can't penetrate 3,000 kilometers into Jupiter's thick atmosphere. It gets completely absorbed in the very top layers. So, The energy source must be coming from within. Jupiter is a hot planet on the inside. It actually radiates more heat out into space than it receives from the sun. This internal heat, left over from its formation 4.5 billion years ago, slowly churns its way to the surface through a process called convection, like water boiling in a pot. For a long time, scientists thought this convection was the primary engine for the winds. Hot gas rises, cool gas sinks, and the planet's rapid rotation twists these movements into the jet streams we see. But the Juno data threw a wrench in that idea too. The gravity measurements suggested that below the 3,000-kilometer mark, the winds seemed to fade away. It appears that at this depth, something changes. Down there, the pressure is immense, over 100,000 times the atmospheric pressure on Earth. The hydrogen gas begins to behave less like a gas and more like a liquid metal. Scientists believe that Jupiter's powerful magnetic field, generated even deeper within this metallic hydrogen layer, might be acting as a brake. Think of it like this. As the deep winds try to push into this electrically conductive region, they create electrical currents. According to the laws of physics, these currents interact with the magnetic field, creating a drag force that slows the flow down. It's like trying to stir a pot of thick honey with a magnetic spoon. Below this 3,000-kilometer boundary, the planet starts to rotate more like a solid, rigid body. So we have this incredible picture: a surface layer of weather, a massive mid-layer of deep cylindrical winds extending 3,000 kilometers down, and then a deep interior where a magnetic brake stops the show. But the ultimate question remains: how is the energy from the deep interior transferred up to power those gigantic wind cylinders and keep them going for billions of years? The mechanisms are still a hot topic of research. How does the slow churn of convection in the deep interior connect to these fast, organized jet streams above? Are there giant slow-moving convective columns that feed energy into the winds? Or does the energy transfer happen through some other kind of wave or instability? It's a complex dance of thermodynamics, fluid dynamics, and magnetism on a planetary scale. Solving this puzzle isn't just about understanding Jupiter. Jupiter is our archetype for gas giants. The universe is full of them, these hot Jupiters and super-Earths, we rediscovering around other stars. By understanding the engine that drives Jupiter, we learn the fundamental physics of how these giant worlds work. It helps us understand how they form, how they evolve, and what their internal structures might be like, even when they're light years away. The Juno mission continues its daring dives, gathering more and more data with each orbit. Each new piece of information helps us refine our models and get one step closer to solving the deep wind puzzle. It's a testament to human curiosity looking at a distant point of light in the sky and asking, what's going on under those clouds? And then building a machine to fly there and find out. The universe is full of mysteries, but piece by piece, we are pulling back the veil. Thanks for joining me on this journey to the heart of a giant. If you enjoyed this deep dive into planetary science, make sure to hit that like button and subscribe for more explorations into the cosmos. Let me know in the comments what other space mysteries you'd like to see us tackle next. Until then, keep looking up